Now we'd like to know where the center of a distribution is, and that point, also called the mean, is named the expected value. So the expected value of a discrete random variable is what we're looking at. So if we go back to our coin toss example here, we toss a coin twice. On average, how many heads would you expect? So this on average, that's asking, what do we expect? What is the mean? What is the average of the distribution? And we can see it's a symmetric distribution here, and it looks like 1 is at the middle. So I listed our distribution. 0, 1, or 2 heads, they occurred with probability 1, 2, and 4. And the expected value or mean of a discrete random variable is written as mu, or sometimes E of x. E is for expected value, x is our random variable. And you sum up x times the probability of x. So the reason you do this is, just do a little example here. Let's say you had 3 exams and you want to find the mean of those exams. So let's say your exam scores were 80, 100, and 40. Did really poorly on the last exam. So the average of those you would add up and divide by 3. So 180, 220, divide by 3. Well, another way to say dividing by 3 is that you would just multiply each score by 1/3. Well, actually, maybe I should put it on the other side here. So 80 times 1/3, 100 times 1/3, and 40 times 1/3. So we multiplied the score by the weighting. Well, let's say I was going to weight your lowest exam half. Then this would be 80 times, well, if you weight the lowest exam half, then that's like saying, well, there's 2 scores here for every 1 score there. So 2, 2, 1, this would actually be 2/5 plus 100 times 2/5. And then plus 40 times 1/5. So then you can see my weighting, these are multiplications, is less, it's 1/2 of what it was before, or 1/2 of the other exams. So that is a weighted average, and that's what we're doing here. Probability of x, the probabilities you have to add up to 1. Notice the weights here, add up to 1. 2/5, 2/5, 1/5 is 1. 1/3, 1/3, 1/3 is 1. So this is kind of weighted average, where you're weighting by the probabilities. Okay, so let's compute that for this data. So an easy way to do this is add an extra column to your table, which is x times probability. So just multiply straight across. 0 times 1/4, 0. 1 times 1/2, 1/2. 2 times 1/4 is 2/4, which is also 1/2. And then sum these. So the sum, or the total on the bottom, is 1. And that is the sum. Remember, sigma here stands for sum. So you sum up x times probability. So this right here, that is our mean. The sum of the x times probability column. So that's center of the data. What about variation in the data? Well, the variance of a discrete random variable is denoted sigma squared, or expected value of x minus mu squared. So this is the average value, or the mean of these quantities, data value minus mean squared. That's the deviation from the mean squared. And that's what we did when we had standard deviation before, right? We did sum of x minus x bar squared. And then we divided by n minus 1. So, well, instead of dividing by n minus 1 here, we're going to multiply by the probabilities. So we're going to sum up the deviation squared times the probability. So an easy way to do this is to add one more column to your table here, x squared times probability of x. And so let's see here. x squared, 0 squared is 0, times 1/4 is 0. 1 squared is 1, times 1/2 is 1/2. And 2 squared is 4, times 1/4 is actually 1. And so if you add those up here, you get 3/2 or 1.5. And that is the sum of x squared times p of x, which we can show that if you sum up x squared times the probability and subtract off the mean squared, it's the shortcut formula for this, which is the variation. So this is the deviation squared times the probability. But we're using the shortcut formula, so we're figuring this part right now. So that 1.5, so that's our variance. And then the standard deviation, you just take square root. So our variance, sigma squared, is the sum of the x squared p of x, 1.5, minus the mean squared. Our mean is 1, so 1 squared. So that's just 0.5. And then sigma would be the square root of 0.5. And this is about 0.707. So now we know how to do center and spread for a discrete random variable. Now, one thing that we want to consider here once we know spread is we can compare a random variable distribution to Chebyshev and the empirical rule. If x is your random variable and mu is the mean and standard deviation is sigma, then depending on the shape of your probability distribution, we could look at probability that a value is within one standard deviation, so mu plus or minus sigma. For Chebyshev's rule, they just say has to be at least some of the data in there. For empirical rule, it's about 68%. Now, if you're within mean minus 2 standard deviations to mean plus, Chebyshev's rule says at least 3/4 of the data, empirical rule approximately 95%. And then mean minus 3 standard deviations to mean plus 3, Chebyshev's rule, at least 8/9 of the data. For the empirical rule, is 99.7%, so almost 100% of the data. So now that we know mean and standard deviation, we can figure these probabilities or proportions for our random variable. And then we can see how close it is to being a normal distribution. Some discrete random variables are pretty close here, and some are not at all.